Welcome again to today's session. The last talk of today's session will be by Dr. Shahab Fatemi of the Umeå University in Sweden. Dr. Fatemi, he was graduated, he got his PhD training from Kiruna, Sweden. And after receiving his PhD, he went to UC Berkeley to work as a postdoc. Where I think you had done a lot of work there also, on simulation on the moon and so on. Yeah, and he's now back in Sweden. He's working at the Umeå. I was hoping to ask him to tell us about the midnight sun, in Sweden. But he's not now in Sweden, he's in Switzerland. And but still a very nice place. So Shahab, can you start your lecture?
Okay, thank you. Hello, and thanks for inviting me to this mini moon seminar. I'm Shahab Fatemi. I'm a researcher at the Department of Physics at Umeå University in Sweden, but at the moment, as you said, I'm just visiting Switzerland for a short time. And today I'm going to talk about the electromagnetic sounding of the lunar interior. This was the project we started nearly 5-6 years ago with some of my colleagues. I've listed them down here in this list, and I should thank them for their collaboration and for their interesting discussions about this topic. Today, my talk would be given in two parts. The first part is about the principles of the electromagnetic sounding, with a main focus on Apollo observations. And the second part, I will explain the results we have got so far on this interesting topic using simulations. So, as you know, the moon, with a radius of nearly 1,730 kilometers, does not have an atmosphere, and instead it has a very thin collisionless exosphere. Since there is no atmosphere, the surface temperature varies quite a lot between the day and night, and at the moment, the moon is utterly dry, and there is no evidence of liquid water flowing on the surface. However, there are water ice, mainly concentrated in the permanently shadowed craters over the moon. I guess from the previous talks, you have already seen about the moon, and you have also seen about the magnetic fields. We have heard that the moon does not have a global magnetic field at the moment, but it has a remnant crustal magnetizations, which are already discussed by Saito-san. And the moon, as the brightest object overnight, has always been of our interest to learn more about it. And for example, you can see this beautiful sketch from Galileo Galilei from nearly 4 years ago, which always fascinates me with how much of a detail he could have drawn this picture of the moon. After the golden area of lunar exploration back in 60s, there is again a growing interest in lunar exploration. We have always been curious about the moon. We have always been curious about the formation of the solar system and other solar system bodies, especially the moon, because it's our closest neighbor. And we want to know where it did come from and how it did form, and what is its connection to the formation of life on Earth. There are several theories about the lunar formation, one of which is the so-called the giant impact. In that theory, it has been suggested that the large impactor has impacted the moon, and then the moon was accreted from the remnants of that large impact, and then it was formed, perhaps at different orbits than it is at the moment. Resolving the interior structure of planetary bodies is of fundamental importance for understanding the origin and also the evolution of the planets, as well as the moon. And doing such a study would bring insight into condition for the present conditions of the early solar system, as well as the current situation. This illustration that you can see here, it shows a summary of what we currently know, or actually I should say what we think we know about the lunar interior, which is an integration of nearly 5 decades of observations, as well as data analysis, model development, theories. Today, we know that the moon has a very thin and highly resistive crust, and it has a conductive mantle. But the core structure is still not known, and it's still under the debate. There are some suggestions stating that if the moon has a core, then it should be smaller than 400, 300 kilometer in radius. Different methods, or I should say different techniques, have been applied to investigate the lunar interior, including the spacecraft observations of topology and gravity. For example, this very nice image, this very beautiful picture from Grail observations that's showing the gravity of the moon, as well as the magnetic field observations by the spacecraft, and in situ observations of seismicity, magnetic fields, as well as the heat flow experiments on the lunar surface. And there's been also Earth-based laser ranging measurements. So this presentation, I would only focus on the magnetic field observations and on the electromagnetic sounding, mostly measured on the lunar surface by Apollo experiments. And some words about the electromagnetic soundings. Electromagnetic sounding, or EM sounding, is a very well-known, well-developed geophysical method that has been applied to explore the interior of the Earth. The moon has been also used for the Galilean moons of Jupiter and recently for Mercury. I have listed some of the references. If you are interested to read more about these, you can go and see that these references. These are not the original, but they are mainly the review or the papers that have gone into the details of this topic for any of these specific objects. The principle of the electromagnetic sounding is rather simple and straightforward, and it is by monitoring the electromagnetic response of conducting matter to incident electromagnetic fields. Well, to be honest, it's not as simple as it's thought. I would show you later in my slides that it's by far more complicated. The electromagnetic fields have 2 measurable components. That's the electric field and the magnetic field. These fields are in general functions of position, as well as time in seconds, or frequencies, either in hertz or if it's the angular frequency. And these are the measurable components that would help us to sound the interior of bodies. Generally, the electromagnetic sounding response of a body may be observed in time or frequency domain. We can do the analysis in either of these. When a time-varying magnetic field passes an electrically conducting body, here for our interest is the moon, and induced eddy currents will be generated to oppose the change in the inducing field. That has been also shown in this cartoon. It's a very simple one. It's a classical one. But note that we need an inducing field, which is the source for the electromagnetic induction. These fields would decay with a characteristic time constant of tau. It's often shown by tau. If it's in the unit of seconds, then it's a function of the mu naught sigma L squared divided by 2 pi. Mu naught is the permeability, sigma is the conductivity as a function, is a conductivity, it's Siemens per meter, and L is the characteristic length scale, and if it's divided by 2 pi, then we would get tau in seconds. In practice, the time decay is comprised of sum of time constants, so it means that this can be expressed alternatively in the frequency domain as a transfer function, h of f. Here it's shown, where it's a function of an induced function and the source function. So here, h of source is the Fourier transform of the inducing magnetic field, and h of ind is the Fourier transform of induced magnetic field as at a specific frequency f. The diffusive penetration of the electromagnetic wave is approximately given by the skin depth, shown here by omega. And it's a function of the conductivity as well as the frequency of the wave that is penetrating into that conductive matter. Some words about the different measurement techniques in electromagnetic sounding. All of them have been reviewed in a very nice paper by Grimm and Delory in 2012. I think it's in Advanced Space Research Journal, if I'm not mistaken. Generally speaking, there are 3 different methods listed here. It's the transfer function, the geomagnetic depth sounding, and the magnetotellurics, MT. So one method is the transfer function. In the transfer function it's a vector, and it has a radial and tangential components. So if we go and calculate the ratio between the radial and the tangential components of the transfer function, we can come up with the resistivity profile. Similarly, if we only measure the ratio between the radial components of the magnetic field and the tangential component of the magnetic field, we can come up with a similar. Here is the resistivity. It's not. It's the resistivity profile. Similarly, with the magnetotelluric methods, if we go and calculate the ratio between the orthogonal components of the electric field and the magnetic field, that's why it's shown by I and J, just to emphasize that these are the orthogonal components. Then we can also calculate this rho, which gives us the resistive profile of a body. But in reality, or well, in ideal case, these methods should give us similar results, similar responses. But of course, these are the different methods based on the availability of each of these components and the observations. As I said, for electromagnetic sounding, we need sources. So 2 main natural sources exist for the moon. The moon is in the Earth magnetotail lobes for about 4 days per month, which provides relatively smooth time-varying fields that is approximately spatially uniform at the scale of the moon, in the size of the moon. And the second source is the magnetic field in the solar wind, to which the moon is exposed for most of its orbit around the Earth. It's nearly 75% of the time the moon is immersed in the solar wind. In practice, many useful Apollo data were acquired when the moon was in the magnetosheath. The existence of plasma by itself complicates the induction, which I will explain it in this presentation. But you have also seen from the previous talks, for example, I think it was the talk given by by Jasper Halikas in the first series of the simulation, in the first series of the seminars last year, and I guess by the earlier talk by Shasui, that the surface of the moon is a perfect plasma absorber. So when the solar wind is coming and interacting with the surface of the moon, it's mainly absorbed, and then it forms a plasma wake, which it would be filled in later. And the main reason for the formation of this is because of the plasma absorption, as well as because of the plasma is supermagnetosonic. So this vacuum region forms at low altitudes near the lunar night side. I will come back to that. And as well as the existence of the plasma on the day side and the formation of this lunar wake downstream, they would alter and they would change the signals of the electromagnetic induction. I think I would show it in coming slides. Some words about the Apollo and Explorer 35 magnetometers. The Lunar Surface Magnetometer, LSM, was a fluxgate magnetometer, and it was deployed at 3 different stations on Apollo 12, I think Apollo 15 and Apollo 16 sites. It was primarily designed to measure the magnitude and temporal variations of the magnetic field on the lunar surface to collect and yield information on the electromagnetic characteristics of the lunar interior. Simultaneously, the interplanetary magnetic field in the lunar environment, it was monitored by Explorer 35. Here you can see the orbit of Explorer 35 around the moon. And Explorer 35, it was far away, standing far away from the moon and from any of the disturbances from the moon. So it was a nice way of measuring the source for the magnetic field that was coming and interacting with the moon. And then later, the signals from the moon, it was observed and it was measured by Apollo instruments, Apollo magnetometers on lunar surface. The lunar surface magnetometer, along with Explorer 35, were measured to study the properties of the lunar interior and the lunar environment, and specifically they have some major findings including the electrical conductivity, the temperature and structure of the lunar mantle and core, as well as the magnetic permeability and the iron abundance in the mantle. The surface remnant magnetic fields, it was one of the major findings, explorations by these 2 nice missions, as well as the lunar electromagnetic environments. Apollo electromagnetic sounding were conducted from both dayside and nightside point of view. The dayside observation utilized continuous streams of the magnetic fluctuations and turbulences in the solar wind, enabling long periods of data collection, and it was ideally suited for the frequency domain analysis. There are a bunch of references here. If you're interested to go and read more about the dayside sounding, you can find these references here. And the night-side observations mainly relied on the distinct events. For example, if there was any strong transients in the solar wind, that was analyzed mainly in the time domain. And that was the main, the major path for the night-side electromagnetic sounding, which was mainly well done, and you can go and read more about it in these nice series of papers. However, as I said before, and as you can see in this illustration, then the induced magnetic fields are highly affected by the effects of the solar wind. On the night side, the fields are suggested to be confined on the day side. sorry, on the day side, the fields are confined because of the existence of the solar wind pressure, but on the night side, the fields can extend further downstream because, as I also said, a vacuum would form at downstream in the lunar night side that allows the extension of the induced magnetic fields into the vacuum region. So we would see the results from both of these studies, both in the day side and in the night side, and discuss the effects and the differences between the two methods. This figure, I've picked it from a paper by Dial and Parkin, 71. It's one of the examples, or I should say it's one of the best examples of time domain structure from magnetic induction on the night side. The inducing field, it was measured by Explorer 35. It's shown here on the left. And Apollo fields on the surface, it was measured, and it's shown here on the right. The magnitude of the fields are in the top panels, and the following panels are showing the radial components of the magnetic field and the following tangential components. One is the eastward component, one is the northward component. Here in this observation, we do see that the moon has been hit by a magnetic discontinuity, and then if we look at the radial component, and if we focus on the radial component, we see that there is being observed with a very nice decay of the fields on the surface at the Apollo site. The decay time, if we compare the decay time with the original transient of the fields, it takes more than a few minutes. The time here is in the units of minutes. So by measuring this decay of the magnetic field, Dial and Parkin have been able to suggest the interior profile, the interior conductivity profile of the moon. But this was one of the examples of the observations. They had more than tens of different observations, and then they compiled all of these together, and they came up with the profile for the conductivity of the moon. This was the approach that was taken in the night side, and it was done in the time domain, as you see. So some words about the principles of how they did it. They made a two-layer model. This model is one of the most simplest one that you can come up with. The principles of this method is quite straightforward and easy, and it was relatively also easy to solve it theoretically. In this method, they assume that there is a uniform conductive sphere with the radius of r1 and with the conductivity of sigma 1. And this sphere is surrounded by a highly resistive layer. And here is the surface of the moon. So this RL it shows the radius of the moon. So the thickness of this layer is RL minus R1. They assume that the moon is in vacuum. They assume that there is no plasma, and the changes in the upstream was observed. It was assumed that there is a step function. I think it's missing here. The changes in the upstream magnetic field is a step function they assumed, and the solution to the field changes, it can be obtained by solving this Faraday's equation. So if you go and solve this one, this equation by making these assumptions in the spherical coordinate system, you will come up with this solution. This is the solution they made at BA. This stands for example, the Apollo measurements, the magnetic fields at the Apollo landing site. And delta BE, that's the change that has been observed by the explorer at an orbit. That means that That's the subtraction between the final component of the magnetic field and the initial component of the magnetic field. And it's been then added by the final components. So by solving this one, you can calculate and estimate the magnetic field measured at the lunar surface by Apollo. And as I said, in this method, they assume that the moon is in vacuum. So there is no effect of plasma. Then it doesn't matter, for example, in this example, if the plasma is coming from, well, it should come in this direction, for example, then the response on the day side and the night side would be kind of identical. It wouldn't make any distinctions between the day side and night side. But we know because of the existence of the plasma pressure, the day side response would be completely different compared to the night side. So this method is, for this reason, it's more suitable for the night side sounding, because even at the time, Dial and his colleagues, they knew that the effects of plasma should be considered, but since they were in vacuum and they knew that this method is more suitable for vacuum, then they applied it for the night side sounding. Let's look at the solution. This is the results of that function that I showed you. And if you look at this more carefully, it sort of reminds us the function, the solution we get from a magnetic dipole. So it can be also represented, the solution can be also represented by a dipole, but that's indeed a decaying dipole. The moment of the dipole is decaying by time, t, with this exponential function. If the moon is hit by, for example, a step up or a step down function, these are the solutions we get from that theoretical, from that theory. The middle panel shows the radial response, and the bottom panels show the tangential response. In the radial response, we can see this decay. For example, for a step up, it slowly ramps up and then exponentially goes up, and it reaches to the final asymptotic value. But for the tangential, there would be a peak, a high peak. That's the maximum. It would be nearly 50% higher than the initial step function amplitude, and then it would be decayed. And then different lines here show the solution for different ratios between this R1 and RL. If they assume, for example, R1 is equal to RL, which is extremely large, it's this solution, then you would get a longer time to reach the final solution. And if the ratio is smaller, then it would immediately reach the final value for the amplitude of the step function. And the horizontal axis, it shows time as the function of sigma 1. As the function of the decay time, based on the conductivity of the interior they have assumed. So by doing all of these and by knowing all of these theory, as well as by having this nice set of observations, for example, Dial and Parkin, they try to find the best fit into the Apollo observations. Here is the spiky line, it shows the Apollo observation, the radial component, and the dashed lines show the solutions from the theory. And they found the best fit to the Apollo observation by assuming the interior conductivity of 1.5 times 10 to the power of minus 4 for a large conductive interior. They assumed the uniform body here that I showed, and we assume that it's a conductive. It's nearly 95% of the size of the lunar radius. So it's a very large conductive body with the average conductivity of 1.5 times 10 to the power of minus 4 Siemens per meter. They also tried to fit it into a 3-layer model. And that 3-layer model, of course, it was by far more complicated to come up with a theoretical solution. So they assumed a core and then a highly conductive core, and then another conductive layer, and then surrounded by a highly resistive layer as the crust. So that's the more geophysical method, or more acceptable method in terms of the geophysics of the interior. Here I only show the results. They assumed that the first layer has a conductivity, should have a conductivity less than 10 to the power of minus 9 Siemens per meter. And it's a very thin layer, and then followed up with a mantle, or almost say the mantle, if I'm allowed. Then this layer, or the inner layer, the intermediate layer, it has the conductivity of 10 to the power of minus 4 Siemens, and the core, they found the core to be a very large one. It's nearly 6.6 lunar radii, with a conductivity of 10 to the power of minus 2. So some words about the Dayside electromagnetic sounding. So here I show an example of the Dayside transfer function observed by Apollo. Here it shows the amplitude of the transfer function. This circles show the radial component of the transfer function, and the triangles and squares show the tangential components. Here in this example, I picked it from Sonnet 72. They do see that the radial component is pretty constant and is near 1 for all different frequencies. And they observed an amplification for the tangential component. All of these would suggest that the radial component is kind of pushed down to the surface, and all the induced fields are pushed down to the surface. And what they can see is only the tangential, that's the horizontal components of the fields. And they could not see any changes or any effects of the radial components. And that's, again, because the solar wind dynamic pressure is by far higher than the magnetic pressure made by the induced fields that pushes all the fields on the day side down to the surface. And in this example, for the in this example for the Dayside transfer function, they did it in the frequency domain. They could not see any signal or any effects of the radial component that was extending out from the surface, but instead they could see some amplifications in the tangential components. In reality, the results from the Dayside and the Nightside sounding, either used in the frequency domain or the time domain, should come up with similar solutions for the interior. But surprisingly, when Sonnet and as well as Schubert, his colleagues, in other series of papers, did the frequency domain analysis on the Dayside sounding, they found the interior of the moon nearly an order of magnitude smaller than what the people have done from Nightside time domain analysis, which is kind of surprising. But at the same time, if you think about it, it's not, it shouldn't be that surprising, because here in the Nightside, you do not assume and you do not consider the effects of plasma, but in the Dayside, you have considered the plasma effects. To wrap up with all the different observations and all the different theories applied to the lunar interior, this is our current understanding of the lunar interior conductivity. This plot shows the summary of all the different methods applied and different results got either from the theories, from the observations. And if we look at it, then the best fit we can get is actually this Pavlov function that shows the conductivity of the moon. And this is apparently the best fit we can get. And this is what we, at the moment, we think we know about the interior conductivity of the moon based on previous observations. And here, well, there is a large jump. Of course, we know all the models kind of agree that the crust is highly resistive. So this is the radius. Here is the center of the moon, and here is on the surface, normalized to the radius. And on the surface, the conductivity is extremely small. Well, here it goes down to the -4, but most of the observations go, it should be 10 to the power of -9 or even 10 to the power of -12, even suggested. So let's talk about the solar wind. We have seen about we have talked about the electromagnetic soundings, and we have seen some of the observations by Apollo and discussed the results. But I've been always talking about the solar wind, and I was saying that the solar wind is important, but it's been neglected in, or oversimplified, I should say, in most of the previous electromagnetic sounding methods applied to the moon. But some words about the plasma. Well, one of the most important thing is in this, if you only focus on this plot, on the simulation obtained from my simulations, the solar wind plasma is coming from right to left. And as its impact the surface of the moon is being removed and then makes a vacuum region behind the moon. So to maintain the pressure balance between the vacuum region here at low altitudes close to the surface of the moon in the night side and outside of the lunar disturbances. We do see here, we do have plasma. Here is no plasma. So to maintain the pressure balance, the magnetic field should go up. So the magnetic field intensity would increase here naturally. And to fulfill the divergence of B equal to 0, the magnetic field should be reduced somewhere. So this is the effects of the reduction is just to fulfill that div B equals 0. And all of the perturbations are kind of confined within the characteristic Mach cones. Here the dashed line show the characteristics of the magnetosonic waves that are propagating perpendicular to this plane. And all of these perturbations are confined within these Mach cone area, this supersonic, supermagnetosonic Mach cone. Since the magnetic fields would increase and also followed up by the decrease of the magnetic fields, it shows that there should be some currents, some electric currents. So with our simulations, we calculated those currents, and we came up with this illustration, this cartoon showing the topology, one scenario of the topology, because this the currents would certainly change as the orientation of the magnetic field, the IMF, would change. So for the condition that the IMF is perpendicular to the solar wind, the IMF is pointing down to the surface, this is the current system we get in the lunar wake. So the lunar vacuum region is surrounded by the diamagnetic currents shown by J1 here, and then the Mach cone boundaries are also confined by the currents. We call them the rarefaction currents or the Mach cone currents. So all of these currents would confine the magnetic fields inside the Mach cone area. So what we think is that the existence of these currents should perturb the induced magnetic fields, and it should affect observations. It has been suggested by series of previous papers, especially those during the Apollo time, that the induced magnetic fields are confined both in the dayside, as well as inside the Mach cone area. So we wanted to test that. We wanted to see if the induced magnetic fields are confined on the dayside and night side or not. And what is the effects of those night side wake currents that we have seen from our simulations in the confinement of the induced fields. So in order to do that, we used our simulation, our plasma model, and we made a very simplified assumptions. We took these results and we simply applied in the center of the moon a dipole moment representing the induced magnetic fields of the moon. So the dipole moment that can be simplified with this approximation. If this delta B is the change of the magnetic field and this RC is the radius of the conductive layer, then we can simplify the induced magnetic fields with this dipole moment. Based on the Artemis observations, we made this histogram of the observations showing the change of the magnetic fields. And here it shows the number of events per year per 1 nanotesla bin, and it was averaged over, I think it was over 5 years. And that's why for some of the bins it's lower than 1, because it's averaged over 5 years. So we do see that it's possible that we do get a magnetic field changes of more than 10 nanotesla, even more than 20 nanotesla at a time. So that's a large change in the magnetic field. And then if we go and apply this magnetic field changes into different conductivity for the interior, for different radius of the conductive layer for the interior of the moon, then we can calculate this map of induced moments. Based on Dial had suggested that the core should be standing at nearly 0.6 lunar radii, and then later Russell had suggested that the core should be standing at nearly 0.2 lunar radii. And then if that is so, and if the moon with either of these core sizes is impacted with one of these large changes of the magnetic field, then the induced dipole moment should fit in between these two lines. And to guide the eyes, I've shown the one of the intensity of the induced moments, that's 10 to the power of 16, and it should be perhaps higher. So we took this 10 to the power of 16 moment and put it at the center of our simulations and ran our simulation to see what would be the effect. Are the magnetic field induced fields from this, are the fields from this dipole moment confined both in the day side and in the night side or not? And these are the results of our simulation. So the first panel here on top, on top left corner, it shows the results of our simulation when the induced dipole moment is not included in the moon. We do see that all the magnetic fields, here it shows the magnetic field ratio, all the fields are confined within these characteristics wave boundaries that we have shown. And then in the middle, it shows the solution when the dipole moment with the moment of 10 to the power of 16 is included in our simulation. By looking at it by eyes, we do not see much of a difference between this simulation and that one. But if we took the difference between the two, then the results would be very interesting. First of all, we do see that there is no indication of the induced magnetic fields on the day side, which means that the day side induced fields are confined in by the existence of the solar wind dynamic pressure. However, we do see that there is some leakage of the induced fields outside of these Mach cone boundaries, as well as inside the Mach cone boundaries. It doesn't tell us that all of these fields are confined within this vacuum region. The vacuum region is shown by this blue area. So the fields are certainly, the induced fields are certainly going outside the vacuum region, and they should be possible to be observed. Another nice thing, I've zoomed in this graph here, is to see that there is no sign of the induced fields upstream in the day side, but in the downstream, we do see that the induced fields are kind of dipolar shape, which reminds us that this cartoon back in 60s is still valid and it's a correct one based on our simulations. But here is another example. I think I'm running out of time, so I should speed up a little bit. As another step for our natural step for our analysis was to apply a time-dependent model. In the previous results, we applied a dipole moment inside our simulation. But then we said, okay, let's develop a model that can handle the interior conductivity of the moon or any other body, and then see what would be the results. So we developed a model that's a hybrid model. It runs on graphic cards. It's a time-dependent model, and it includes the multi-layer interior profile of an object with and without the heterogeneity. It can be uniform, it can be non-uniform. And we solve the magnetic diffusion equation for the interior. Here is an example for the test of our simulation against the theory. We made a step-up function. It's shown by the black, and the solid lines show what the theory tells us in vacuum. And the dots show the results of our hybrid simulation, again in vacuum, when the plasma effect is not included. It shows that the model has been able to capture the solution for magnetic induction of an conductive interior. So we made a setup. We made a 2-layer model into our hybrid simulation. We made a very conductive layer with a radius of nearly 1,600 kilometer. That's R1. With a surrounded by a resistive layer with a conductivity of 10 to the power of minus 8 Siemens per meter. And we made 3 different conductivities for the interior. We made the interior highly conductive with a 10 to the power of minus 8. And we made another simulation with 10 to the power of minus 4 and 10 to the power of minus 3 Siemens per meter. This is more close to what Dial and also Schubert and Sonnet has found for the interior based on the Apollo observations. We ran our simulation and we made a kind of a moderate magnetic discontinuity with a magnitude of 8 nanotesla. So the upstream magnetic field has changed from +4 in one direction to -4, and that's an instantaneous change. And the solar wind parameters applied into the model are kind of a nominal typical conditions. And here are the results. The top panels, the color shows the intensity of the magnetic fields. The top panel shows when the moon, the interior of the moon is highly resistive. So that's 10 to the power of minus 8. The middle one is when the interior is slightly conductive. It's 10 to the power of minus 4. And the bottom one shows when the moon has a conductivity of 10 to the power of minus 3 Siemens per meter. From the left to the right, it shows the time series of our simulation. Here, the magnetic field is pointing upward, and then later here in this time, we see that the magnetic field orientation has changed from upward to downward, and then it has hit the moon and it has passed. When the moon is kind of resistive, there is not much of an effect of magnetic field induction in the interior, but as we go down with higher conductivity, we do see that the moon is responding to the changes of the magnetic fields and trying to oppose the changes. And it depends, the decay time also depends on the conductivity. There are also some effects if the interior conductivity is high, then we do see that there are some effects from the moon that can be observable outside the lunar wake. But this is for a kind of exotic condition. That's 10 to the power of minus 3, and the interior size is quite large. It's nearly 0.9 lunar radii. But for the conditions that, for example, Dial and Sonnet has came up with, we do see that there are some small changes outside the wake. That's perhaps the indication of the induced fields that can be observable, but the signal is very small. It's pretty weak. It's perhaps not that easy to be observed by spacecrafts. As the last part of the talk, we try to compare our simulations with those theories that Dial came up with. So we made 2 observers. Both of them are in the night side. One exactly at the midnight plane, that's observer 1. And then we made an observer 2 with 45 degrees standing between the midnight and the terminator. So the solar wind is coming in this direction. It's coming along the minus x-axis, and the change of the magnetic field was only along y-axis, which was perpendicular to the flow of the solar wind. By observing the field changes in these 2 locations, observer 1 and 2, we try to compare our hybrid simulations when the plasma effects is included with those theoretical results from Dial that have not considered the effects of plasma. And these are what we got. So the left panel results, they show the results for the observer 1. Sorry, I should have put the note title on top, but anyway. And the right-hand side one shows the results from the observer 2. If we are deep in the night side, if we are really in the vacuum region, we do see that there is not much of a difference between our simulation results and the theories. Our simulation results are shown, our hybrid simulation results are shown by green, and the dial theoretical results are shown by these dashed lines. We do see that when the moon is highly resistive, of course, there is some time delay between the moon response to the magnetic field changes until it comes to the step-up function. But the results kind of matches with the theory, as well as when they do have a conductive interior, the decay of the radial component of the magnetic field kind of follows nicely with the theory that the dial has used to analyze the Apollo data. But when we are off the night side, when we go somewhere that the plasma effect is perhaps important in the night side, that's this point, that's at 45 degrees away from the central wake, then we do see that our simulation results in terms of the decaying is kind of similar to what dial has got, but the amplitude of a signal is nearly 2 times higher, 2 times larger than what theory tells us that we should get. And we think this amplification of the signal, as well as the change, perhaps change in the decay time of the signal, is the effect of plasma, and it's because of the effects of those currents that are forming in the lunar wake that would prevent some of the changes that is occurring in the magnetic induction, and also amplifies the magnetic field changes in the lunar interior. So to wrap up, as a summary, after half a century of exploration, we still don't know much about the lunar interior. That's kind of a fact. Of course, there's been a lot of nice work that has been done, but still the work is ongoing, and we still need to do more observations and more investigations. Electromagnetic sounding is a powerful tool to probe the interior of a planetary body. But I would like to emphasize that the solar wind plasma plays a crucial role in changing the structure and topology of the induced field, as I showed in my last slides. So the simplified, for example, those vacuum approximation theory models are certainly helpful, or they were helpful, but not anymore, because we need to consider the effect of plasma, and in order to do that, the self-consistent models should consider both the induction and plasma effects when we want to go and analyze the lunar interior, the inductive response of the lunar interior. I think I would stop here, and thanks for your attention, and I would be happy to take your questions.
Thank you so much, Shahab. I can see that you have worked on this for a few years, you know, in a series of papers. You go read deep in detail. And for the people in the audience who are interested in electromagnetic, you know, it will be a very nice problem to work on. So anyone has questions for Dr. Fatemi? I think it's not easy to find people to explain this to us. Okay, then I asked a couple questions for them. You know, the first thing is this: you know, after all this, are you able to tell us what is the size of the core?
Oh, well, the core is the most tricky one. The core, I cannot tell anything about it. First, I think we should mostly rely on the latest observations, for example, by Grail. Mm-hmm. And those observations, they tell us, for example, if there is a core, they say that the size of the liquid core is, or the outer layer of the core is something around, something smaller than 400 kilometers. And for the inner core, it's very interesting. In the paper, you can see they say it's 0 to 280 kilometers. So it's really not known. But I think that's the most tricky one. And if we want to do the sounding, the EM sounding, specifically for the core, we require to have a very low frequency waves. And people, for example, like Lon Hood, they have done that. And they also came up with these suggestions that the size of the core is something around 300, 400 kilometers if it exists, but it's extremely small.
But with seismometer, you know, seismology, can you tell the core size and origin?
Well, with those, they have already done it all the way down to the moonquake lines. That's kind of perhaps the upper, or maybe down to the lower mantle. They have not been able to go further below. That's the max they have been able. But I think I hope and I guess we will find out more with the upcoming missions in future. Then we would understand a lot more about the interior.
The second question is that, with this kind of methodology, do you think you could apply the same thing to Mercury? Even Mercury itself has its only intrinsic dipole field.
I don't know how to answer this because Mercury has advantages and disadvantages. Mercury's core is thought to be extremely large, so the effects of induction would be much easier to be seen. Either on the surface, well, we don't have any instrument, anything on the surface, but also at some altitudes above the surface. But at the same time, the existence of the intrinsic magnetic field complicates the problem. And the magnetopause, for example, the magnetopause of Mercury, it stands extremely close to the surface. So that's at another layer of currents that would perturb the induced currents. So it makes it by far more complicated, although the size of the core is much larger and we are expecting to be much easier to see the effects of the core and the interior. But it's not, because, well, the solar wind is more harsh and the intrinsic magnetic field of Mercury complicates everything.
Okay, because I know I read papers by people in Braunschweig about the metaspheric current could even go down, into the core and forming a current system. That sounds very interesting. And for yours, in the case, because you don't have a dipole field, intrinsic dipole field, so the current could not really go, connected to the core. You have to go back to the solar wind, according to your current system. Okay. Anyone have thought about question to ask Dr. Fatemi? Then I would end the talk by asking him to do two things. The first thing that if you see Peter Woods, and please give him my regard, and tell him that I'm going to invite him to give a talk. And the second thing is that, and then you remember you have to give a talk on the ion fascination by the primordial solar wind. Still, that is another topic you're working on, right?
Sure.
I mean, I think that one is a more easier to understand than this one. This one, there's no kind of medical treatment, right? But it's very, very important. That's very important. Very good. I think you have done a very good job.
Thank you.
Yeah. And you have any question to ask the audience?
Oh no. It was good to see you, and thanks again for inviting me.
Yeah, I mean, the great pleasure. And I will write to you, remind you that to invite you again to give a second talk, but not right away, not next week, not next week, but perhaps in September, October. Yeah, right. And have a good summer. Have a good summer.
Thank you.
Yeah.
Thank you.
Yeah.
You too.
Yeah. Bye bye. Take care. Yeah.
Okay. Yeah. Bye bye.